slides, we have seen about the Cauchy's integral formula, Cauchy's integral theorem, Cauchy's integral formula, and some problems related to Cauchy's integral formula. We have seen how to find the value of the integral by using the Cauchy's integral formula. Now let us see about zeros of an analytic function. A zero of an analytic function f of z is a value of z at which f of z is equal to 0. If f of a is equal to 0 and f dash of a, the derivative of f of z at z equal to a is not equal to 0, then z equal to a is called a simple zero of f of z or a zero of the first order. If f of a is equal to f dash of a is equal to etc. and goes on, f power n minus 1 of a is equal to 0 and f power n of a not equal to 0, then a is called a zero of order n. For example, we can see some two results in the slide. Now singular point, what is meant by singular point? A point at which the function f of z is not analytic is called a singular point or a singular point of f of z. For example, z equal to 2 is a singular point of f of z is equal to 1 by z minus 2. Equating the denominator z minus 2 equal to 0, we get z equal to 2 as a singular point. Now f of z is equal to 1 by z square plus 4. So when we equate z square plus 4 is equal to 0, then we get z is equal to plus or minus 2y. We get the complex roots. Now let us see about the types of singularities. The first one, isolated singular point. If z equal to 0 is a singularity of f of z, and if there is no other singularity within a small circle surrounding the point z equal to a, then z equal to a is said to be an isolated singularity of the function f of z. Otherwise, it is called non-isolated. For example, f of z is equal to 1 by z minus 1 z minus 4. It will have two isolated singular points, namely z equal to 1 and z equal to 4. Now let us see about the poles. Let a function f of z have an isolated singular point z equal to a. F of z, it can be expanded in a Laurent series around z equal to a. So how to write in the Laurent series expansion? Already we have seen Laurent series. So we can able to write it in the form f of z is equal to a naught plus a1 into z minus a plus a2 z minus a whole square plus etc. b1 by z minus a plus b2 by z minus a whole square plus etc. In some cases it may happen that the coefficients bm plus 1 is equal to bm plus 2 etc. equal to 0. Then the above equation will reduce to the form f of z is equal to a naught plus a1 z minus a plus a2 z minus a whole square plus etc. b1 by z minus a etc. plus bm by z minus a whole power m. Then z equal to a is said to be a pole of order m of the function f of z. Now when m is equal to 1, the pole is said to be a simple pole. In this case, f of z is equal to a naught plus a1 z minus a plus a2 z minus a whole square plus etc. Now for example, f of z is equal to 1 by z minus 4 whole square into z plus 5 the whole cube. Here z equal to 4, it is a pole of order 2, and z plus 5 is equal to 0 gives you z equal to minus 5, and it is a pole of order 3. Since we have z plus 5 power 3, therefore the order is equal to 3. Now for z equal to 4, the power is 2, therefore the order is equal to 2. Now let us see the next type, essential singularity. If the principal part contains an infinite number of terms, then z equal to a is known as essential singularity. Here f of z is equal to e power 1 by z. Now we can expand this e power 1 by z by using the formula e power x. E power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. So here x is nothing but 1 by z, so 1 plus 1 by z by 1 factorial plus 1 by z square by 2 factorial etc. up to infinity and it has z equal to 0 as an essential singularity, since f of z is an infinite series of negative powers of z. Now next type is a removable singularity. If the principal part of f of z contains no term, that is if bn is equal to 0 for all n, then the singularity z equal to a is known as the removable singularity of f of z. In this example, f of z is equal to sin z by z is a removable singularity at z equal to 0. Since limit z tends to 0, f of z is equal to limit z tends to 0 sin z by z, and it is equal to 1. Therefore, z equal to 0 is the removable singularity. What is meant by entire function? F of z, which is analytic everywhere in the finite plane except at infinity, is called an entire function. For example, sin z, cos z are all called entire function. Even e power z is also called an entire function. Now, meromorphic function. A function f of z which is analytic everywhere in the finite plane except at finite number of poles is called a meromorphic function. Now here is an example given for meromorphic function. Z by z minus 2 into z minus 3 whole square. It is said to be meromorphic function since it fails to be analytic at this poles z equal to 2 and z equal to 3.